Hello there and welcome back to this video series on control systems. In the previous video we have seen the response of a first order system to a unit impulse input, step input and ramp input. In the present video we'll try to solve one problem on time response analysis of first order system. This takes kind of relating mathematics to the physical situation happening in real life. Follow this problem closely, but I would encourage that you watch videos 7, 8, 9, 10 and 11 and the previous two videos 31 and 32 thoroughly. Take notes and keep them handy while you watch this video. That way you'll make the most out of this video. With that, we'll see one problem. This problem is about a first order system which is a liquid in glass thermometer. This thermometer is kept in water at 35 degrees centigrade. We call the temperature of the water to be RT input. The number shown on the thermometer as the output. At time t is equal to 0, that is when we are beginning this experiment, the time t is equal to 0 and both RT and CT are steady at 35 degrees centigrade. Then we take this thermometer and put it in some other liquid bath, a liquid bath at 110 degrees centigrade. Initially it is at 35 degrees centigrade in this condition shown here, and then we take out and suddenly immerse it in a liquid bath at 110 degrees centigrade. If the thermometer reads 85 degrees centigrade after 8 seconds, compute the time constant of the thermometer. This problem illustrates how we can compute the parameters of the system using time response analysis that we studied. So what happened in the problem is that you have another liquid bath with RT is equal to 110 degrees centigrade, and after moving it into the bath, the output CT started rising and it rose to 85 degrees centigrade at 8 seconds. Okay, we have to find out what is the time constant of the system. We will try to solve the problem by noting that since the temperature is maintained constantly at 110 degrees centigrade after the thermometer is put into a new liquid medium, we say that this input is a step change. Okay, noting that we'll note the what is the first order transfer function, and in time domain it appears like this. Okay, CT is 110, and then we will write it down CT plus tau times dCT over dt is equal to 110. If you take Laplace transform on either side, note that Laplace transform of a derivative is s times Cs minus the initial condition at time t is equal to 0. Go back to the previous slide and see what is the value of C at time t is equal to 0. It is 35. So once you do this, you will write it down and split it into partial fractions and find the constants A and B. Substitute s is equal to 0, you have A is equal to 110. Substitute s is equal to minus 1 over tau because we want to cancel this term. We get B is equal to minus 75 tau. So the Cs is 110 over s and this, and when you take inverse transform, you see 75 e to the power of minus t over tau. In this equation substitute t is equal to 8 seconds and Ct is equal to 75 because that is the given condition to find that the time constant is 10 seconds. This kind of illustrates that all real life problems do not come as equation problems. They come as word problems, that is, they describe a situation and we need to convert it into our controls language or mathematics language. That is the first step. Then it always helps to draw a sketch to indicate the situation and what kind of changes that are coming onto it. That kind of picture really helps a lot to relate the mathematics and the physics going on in the problem. And we have seen that a liquid in glass thermometer is a first order system, and we can compute the time constant of the first order system by conducting a little experiment. That little experiment will give us what is the time constant of the system when we apply what we learned in time response analysis. I think that's all we have for now. Have a great day.